Greetings, everyone. Today we're going to take a quick look at some of the mathematics behind simple harmonic motion. We're going to bring in some trigonometry, and some of you have a pretty strong background in trigonometry. Others maybe have just learned some things this year or are a little more shaky. We're not going to go super deep, but we're going to see a lot of connections to maybe some things that you've seen in math class, and I'm going to give you the kind of final takeaway of what you need to take from it. So it won't take us very long, but we're just going to look at a basic brief overview of how trig functions can be used to describe things that vibrate or oscillate. So one of the big uses of trigonometry in the real physical world. So let's consider a system we should be pretty familiar with so far, the spring mass system. Again, remember, it's not just about boxes connected to springs, but a lot of real life systems have springiness and inertia to them. So really all real life systems have some springiness and inertia. So remember, we got this all important point, this equilibrium point, that if the mass is placed here, that experiences no force. That's kind of boring, it would just stay there. So let's start the mass at a place where it will get a force. So let's say we put it out here. There's some kind of spring connected to the wall. And we know in this position that if I let this thing go, the spring's going to pull it back towards equilibrium. Then it will have some speed and it will cruise right on through. So this should be looking pretty familiar here. If I release it here from rest, then this becomes the amplitude, the positive amplitude. And it's never going to go farther away from equilibrium than this spot because there's a set amount of energy in the spring. And if it stretched out more, then it would need somehow to get more energy in the system. And it's going to oscillate, and it will oscillate the same way on the other side to negative amplitude. It's just going to go back and forth between these two spots once we've let this go. So this is very familiar. What we're going to be looking at here, let's see, we got 1 second period. The time for if an oscillation is 1 complete second. We're going to try to make a map of, and this should seem familiar if we think back to the beginning of the school year, position, velocity, and acceleration for this thing. So we're going to start with the simplest of the graphs first. The graph of position is a function of time. So this is oscillating sideways. We have a horizontal x position here, and then time on our horizontal axis. So what you should be able to do is look at a picture like this and kind of put it together piece by piece, thinking about where it begins and where it goes afterwards. So if I look at this thing is beginning here at positive amplitude. So it begins at a positive position. So at time equals 0, I need to start at a positive position. So I'm going to make this spot here be my positive amplitude. And then this spot down here will be my negative amplitude. So we'll just kind of plot it over some different moments in time. So it starts at the positive position. And it's going to cruise back towards equilibrium. It's going to come to x equals 0. So sometime later, let's say this time here, it's going to be at equilibrium. It's going to cruise right on through to negative amplitude. So I'm going to draw some dots that I'm going to end up connecting here. And it's going to slow down and stop. And it's going to return back to equilibrium again. And it's going to go to positive amplitude. And it's just going to keep on oscillating like that. Okay. So let's see what we got. I'm going to connect my dots. And not with straight lines, but with some curvature, something like this. Now, why am I curving it instead of drawing it as a straight line? It's because these transitions are happening gradually. If you remember, the slope of a position graph is the velocity. So anywhere where I'm at amplitude, it needs to slow down and stop. So it needs to be flat, the places where I'm at positive and negative amplitude. And in between, when I'm at equilibrium, it needs to be going fast. So here it's going fast in the negative direction, slows down and stops, and then goes fast in the positive direction. So those of you who are comfortable and familiar with trigonometry will recognize this function here. This is a trig function. A trig function that starts at positive amplitude is the cosine function. So the equation that describes position as a function of time is going to be a cosine function. X equals the amplitude times the cosine of something. So the amplitude is the height of that cosine function. It's just going to be A. And I'm going to say it's equal to the cosine of omega t. Now this is new, and I'll explain what this means in just a moment, but we see that it depends on time. This trig function varies with time, but we've got this omega term here. Now, it doesn't look like an omega, it looks like a W, right? Like maybe the Wegmans W or something like that. But this is the Greek letter O, strangely enough. Greek letter omega, And we're going to use omega to talk about how quickly our trig function repeats itself. So speaking of that, we can see, I should be able to identify some times in here. I know the period is 1 second, so the time for it to go through one whole oscillation back into here, so that means this is going to be 1 second, one complete cycle. So this would be half a second, and 3/4 of a second, and 1/4 of a second. So we can kind of break it down like this. The function looks like. So this is position as a function of time. Now, what I'm going to do is I'm going to take this relationship and I'm going to try to come up with a velocity relationship that describes this as well. And I can do that either from the position graph, or I could just do it straight up from the picture if that makes more sense. And it should make sense to us both ways. So here's velocity as a function of time. And let's do, I think, maybe the more intuitive way is just by looking at the picture and think about how this thing is moving. So I'm not looking at where it is, but how fast it's going. If I release this thing, it's released from rest. So rather than beginning with a value, it begins with no velocity at all, a 0 velocity. And then I let the thing go, and it's going to begin to pick up speed. And in the picture, I can see it's going to begin to move in the negative direction. So it's going to start to move towards negative velocities then, sometime later. And what I can do to kind of match this up, I'm going to try to match my times up between the two graphs. As I can see, remember that velocity is the slope of my position graph. So here I have a slope of 0. It's flat right here. And then I'm going to have a negative slopes at this time here. So I'm going to have my steepest negative slope and have my biggest negative value at this location right here, my maximum negative velocity. And so that'll be as it passes through equilibrium. Then it's going to slow down and stop. It's going to come to rest again, and that's where this flattens out here at half a second. It's going to come back to 0 velocity. And then it's going to start to move in the positive direction. As it comes through equilibrium, it's going to end up with its maximum positive velocity here where the slope is steep and positive, and it's going to go back to 0 again. So I get another trig function. It just kind of starts and ends a little bit differently. So I'm going to connect my dots with some smooth curve here, curves, something like this. So here's my velocity graph. And so it's the same kind of trig function. It's actually repeating at the same rate. It goes through one whole cycle again in 1 second. So notice that for all of these graphs, position, velocity, and acceleration, they're all going to have a period of 1 second because the cycle happens over the course of 1 second. But in terms of mathematically, we're told that one way of saying this is that they have different phases, that they're shifted in relation to each other. I'm not too worried about dealing with phase and phase angle here. So instead what we're going to do is we're just going to look at this as a different trig function. So if you're familiar with your trig functions, the cosine function starts at amplitude. The sine function starts at 0. Now the sine function can either start at 0 and go up, which is a typical sine function, or in this case it goes the other way. So this is actually a negative sine function. So the equation for velocity is equal to, it has an amplitude as well, but it's a negative sine function. And again, I'm just kind of doing an introductory level to this here. So I'm going to write this as the velocity is negative a omega sine omega t. And so again, we see this thing omega. This omega is telling me how quickly my trig function is repeating. And it shouldn't be a surprise that it shows up in both of these functions because they both repeat at the same rate. So they both have an omega t term here. This is a negative sign because it goes down. It starts at 0. And its amplitude isn't just A. A is a position amplitude. It's an amplitude times omega. And it's a little bit hard to justify that without getting into some calculus. Some of you have taken calc already or have learned some calculus. You'll recognize that what I've done is I've taken the derivative of position with respect to time. Velocity is the first derivative of position with respect to time. And the derivative of a cosine function is a negative sine function. And then you have to take the derivative of the argument, omega t, and that's just going to be, that's where that omega comes from on the outside. If you haven't learned any calc, don't worry about that. I don't want you to, you don't have to know that. It doesn't need to make sense. But I just wanted to say that for those of you who have learned some calculus. Let's take a look at the last graph then, the graph of acceleration as a function of time. And again, you don't need to know calc, and you don't even really need to be familiar with the whole slopes and areas things that we've talked about before. We could just reason this out from the picture. We know that forces cause accelerations. So here, this mass is experiencing a very large force because the spring is stretched out and it's pulling it back in the negative direction. So big negative force. means this thing is going to begin with a significant negative acceleration, a large negative acceleration at this moment. And then as it goes back towards equilibrium, it's going to pass through x equals 0, where there's no force acting at all, so it's going to go to a place of no acceleration. And then as the spring compresses, it's going to go to a place of positive acceleration. So they're all going to be, you're going to see this pattern here with my trig functions. The key is just figuring out where you start, and then the rest can follow from that. You can draw the other dots here for the whole cycle that happens over 1 second. Again, another connection that I could make is by looking at this and saying that acceleration is the slope of my velocity graph. So here I have a negative slope, so I have a negative acceleration. Here I have a 0 slope, so I have a 0 acceleration. Here I have a positive slope, so I have a positive acceleration. It works that way as well. So I'll finish this last graph out. Connect my dots. It's a little hard to do that smoothly sometimes, so just do your best. Okay. And again, we have the same 1 second time for this trig function to oscillate for my acceleration function. And for those of you who have taken some calculus, think about this for a moment. What would, again, acceleration is the derivative of velocity. So if you take the derivative of a negative sine function, that's going to give you what function? Or you could look at the picture and say, okay, it starts at amplitude, just like a cosine function does, but it starts at negative amplitude. So we have a negative cosine. So it's negative, ends up being negative a omega squared cosine of omega t. So again, it repeats itself at this rate omega t. It has an amplitude that's related to a and omega. And again, you don't really have to memorize these functions here. It fits this particular case. But I want to show you what you're going to take away from this is being able to recognize the graphs and see that should be making sense to you. But in order to use this to solve for anything or make this a useful idea, I need some way of defining what omega is. And I'm not going to go into the whole derivation. It actually requires a little bit of calculus, and I'm not going to do that. It's not a calculus-based course. But omega, this should make sense to you. Omega is telling me how quickly this trig function is. How long does it take this trig function to go through a cycle, to repeat itself? And that's going to be related to the properties of my spring mass system. And we know that only depends on two things. The rate at which a spring mass system oscillates depends on the stiffness of the spring and the mass that's oscillating. So I'm going to go ahead and define, and you should put this on your 3x5 card. You're going to need this. Omega is going to be equal to the square root of k over m. Now that should look familiar. We've seen square roots of m's and k's. That's the period and the frequency equations. It's coming from this idea of omega, the square root of k over m, the rate at which this happens. So a very stiff spring is going to make it oscillate fast, have a high omega, and a big mass is going to make it oscillate slowly. This thing has its own name. I've been calling it omega, which it is. It's the Greek letter omega, but the letter stands for a special type of frequency. It's called an angular frequency, and that has the root word angle in it because trig functions repeat through an angle. They repeat through pi and 2 pi and pi over 2. We use angles to talk about where we are in our trig function. So this is a rate at which it goes through 2 pi radians. So the units for omega are actually radians per second, or an angle per second measured in radians. And we can connect this with, and we got to be careful because angular frequency sounds a lot like regular frequency. They're similar, but they're a little bit different. And what I want you to see the connection between the two. So one cycle, if this thing oscillates once, the trig function goes through one cycle, and trig functions repeat themselves every 2 pi radians. So one cycle being 2 pi radians, omega is going to be equal to 2 pi times the frequency. This is the relationship between the two. So omega is equal to 2 pi times the frequency. Here's my angular frequency, and here's my regular frequency. So put that here, angular frequency, and then regular frequency. And you got to be careful about if in a problem solving, it's asking you to solve for one or the other. Just be cautious about which one you're looking for. If you know one, you can easily find the other. They're related to each other. Every time it goes through a cycle, the trig function goes through 2 pi radians. So I want you to know this term. This is going to be important, and that'll help you. If you do know omega, then you could actually plug that number into any of these trig functions and find velocity, position, or acceleration at any time. But the other thing that's extremely useful about these functions that we've come up with, sort of a takeaway from what we're talking about today, is the amplitude, the maximum values of these functions. Now, it doesn't tell me a whole lot to say the amplitude of my position function is the amplitude. I mean, that's the definition of amplitude. But I learned usefully from this, I learned that the amplitude of my velocity function is going to be equal to a omega. So that means that this thing is going to be alternating between positive a omega and negative a omega. So that's why I would want to maybe find omega, because if I multiply that by my amplitude, I can find my maximum speed, the fastest this thing will go. And I can do the same thing with acceleration. Acceleration is going to have an amplitude of a omega squared. So I can use a omega squared and negative a omega squared to find the biggest that my acceleration will be. So I would encourage you, you don't even have to memorize that or anything like that. I would encourage you to put that onto your 3x5 card, your equation card, what our maximum values are going to be. My maximum position is the same thing as the amplitude, and it doesn't tell me anything too sophisticated. My maximum velocity is going to be equal to amplitude times omega. That could be useful for finding a max speed. I could use energy, like potential to kinetic energy, like we were looking at in the last lecture, but now I have maybe a quicker way of doing that. And my maximum acceleration, which I haven't really had a way to find yet, is going to be equal to a omega squared, the size of each of those trig functions, the height, the maximum height. Okay. So that's a lot, and I know that I'm just flying through the trig really quickly. For some of you, that's some review. For others of you, that's maybe stretching you a little bit. But if this bottom piece, if you have this kind of takeaway, next lecture, I'm going to show you some example problems of how to use this, and I think you'll be just fine. So we'll see you there.